This video is a full mathematical walkthrough of the paper, a mathematical theory of semantic development in deep neural networks. We will derive the learning dynamics, connect singular values to developmental stages, explain semantic illusions, and go through the supplementary proofs. The core thesis is that many classic cognitive development phenomena emerge from the exact nonlinear dynamics of deep linear networks. The model is simple, but the dynamics are rich enough to produce stage-like transitions, typicality effects, coherence thresholds, and cross-species representational invariance. We will cover the paper in 4 parts. Part 1 derives learning equations and closed-form mode dynamics. Part 2 explains organization of semantic knowledge. Part 3 analyzes inductive projection and neural similarity. Part 4 goes through supplementary derivations and phase transitions. Training set is a collection of item feature pairs, xi and yi, for I from 1 to p. The deep linear network predicts y hat as w2 times w1 times x. The hidden representation is h equals w1x, and output is y hat equals w2h. Gradient descent gives the online backprop update, with delta w1 proportional to w2 transpose times prediction error times x transpose, and delta w2 proportional to prediction error times h transpose. Crucially, each update is local to one item, yet averaged dynamics will recover global semantic structure. In the small learning rate regime, averaging over one epoch yields deterministic ODEs. Tau dw1 over dt equals w2 transpose times sigma yx minus w2, w1 sigma x. Tau dw2 over dt equals sigma yx minus w2 w1 sigma x times w1 transpose. These are coupled nonlinear matrix equations. The central analytical move is singular value decomposition of sigma yx. Sigma yx equals USV transpose, which decomposes semantic structure into mode triplets: object analyzer V alpha, feature synthesizer U alpha, and strength S alpha. This gives a mode basis in which learning approximately decouples. For tabula rasa small random initialization, the effective singular value of each mode follows a closed-form sigmoid. Alpha of t equals S alpha times exponential of 2S alpha t over tau, divided by exponential of 2S alpha t over tau minus 1 plus S alpha over a 0 alpha. So each mode turns on nonlinearly, with timing set by S alpha. The hidden representations have explicit form. H alpha I equals square root of alpha of t times V alpha I, up to rotation. This means developmental geometry in hidden space is directly controlled by evolving mode strengths and fixed object analyzer coordinates. Now the contrast with shallow linear networks. Their mode trajectories are simple exponentials. B alpha of t equals S alpha times 1 minus e to minus t over tau plus B0 alpha e to minus t over tau. NO sigmoidal switch-like dynamics appears mode-wise. The mode completion time in deep nets scales roughly as tau over S alpha times log S alpha over epsilon. So stronger singular modes are learned earlier. This mathematically generates stage-like hierarchical differentiation when singular values are separated. The paper then uses a hierarchical generative model where features diffuse down an evolutionary tree with rare flips. This creates nested similarity blocks, broad distinctions with large singular values, and fine distinctions with smaller singular values. Deep dynamics then naturally produce coarse-to-fine conceptual differentiation. A striking prediction is illusory correlations. Because outputs are sums over modes, if early and late modes contribute opposite signs to one item feature pair, the prediction curve becomes non-monotonic. Children like semantic illusions can therefore emerge from globally optimal gradient descent itself. Part 2 asks how knowledge is organized after learning. The paper gives explicit mathematical definitions of typicality, prototypes, and category coherence using SVD coordinates. Typicality for item I in semantic distinction, alpha is V alpha I. Equation 13 shows V alpha I equals 1 over PS alpha, times sum over features of U alpha M times object feature OIM. So typicality is a weighted projection of the object onto a mode-specific prototype direction. Dual to this, Equation 14 shows feature synthesizer U alpha M equals weighted average of item features using typicalities V alpha I. This is a clean duality. Typicality depends on prototypes, and prototypes are built from typicality-weighted items. For noisy disjoint categories, the paper derives a closed-form coherence variable, C equals SNR times KO times KF, divided by square root of NO times NF. Only C matters for recovery performance in the high-dimensional limit. The singular value definition of coherence also explains basic-level effects. If between category similarities are negative at an intermediate level, coherence can peak there instead of at superordinate level. So basic-level privilege is a quantitative spectral property, not only a verbal intuition. Beyond hierarchies, the paper analyzes clusters, trees, rings, grids, orderings, and cross-cutting forms. Different probabilistic graphical structures induce different covariance matrices, which induce distinct singular vectors and representational geometries. Part 3 studies deployment of knowledge and neural representational consequences. The key result is that inductive projection is controlled by hidden space similarity geometry. If a novel property is assigned to familiar item I, projection to another item J follows equation 16. I hat M equals Hj transpose Hi divided by norm Hi squared. This is explicit similarity-based generalization in hidden representation space. Conversely, if a novel item is assigned a familiar feature, equation 17 projects other familiar features onto that item by feature space hidden similarity. Together, equations 16 and 17 make induction a geometric operation inside the learned representation. Because hidden geometry differentiates progressively over learning, induction narrows from broad to specific over developmental time. Early representations are coarse and similar, later representations separate fine distinctions. The neural theory section proves a strong invariant. Different networks trained optimally in the same environment can have different single neuron tuning curves, but identical representational similarity matrices. So similarity structure, not individual neuron identity, is the robust code-level object. Equation 18 links behavior and representation. Sigma y hat equals sigma h squared. Hence behavior amplifies the same semantic axes present in hidden representation. This provides a precise criterion for when neural and behavioral similarity should align. Part 4 summarizes key supplementary derivations and thresholds that make the main claims exact. The supplement starts from the squared error objective and derives epoch-averaged ODEs under gradual learning. It then rotates into SVD coordinates and isolates approximately decoupled scalar mode dynamics. This is where the closed forms come from mathematically. Equation S10 gives exact integrated deep mode travel time between initial and final strengths. Equation S11 gives the shallow counterpart. Comparing them formally proves deep mode times are inversely weighted by singular strength, while shallow times are not. The hierarchical generative process is formalized as branching diffusion with sign flips probability epsilon. Overlap parameters QK induce a block covariance matrix, and its eigenvectors are level functions on tree leaves. This makes coarse-defined representational emergence mathematically inevitable. For noisy category recovery, the supplement uses random matrix theory and a BBP transition. Below coherence threshold C less than or equal to 1, recovered analyzers have zero asymptotic overlap with ground truth. Above threshold, overlap grows according to closed-form asymptotic curves. Another important result is global optimality of truncated SVD by Eckart-Young-Mirsky. Among all rank K linear maps, top K singular modes minimize reconstruction error. So category coherence as singular value is also the right notion for efficient representation under capacity constraints. Final takeaway: this paper turns semantic development from descriptive psychology into analyzable learning dynamics. The key bridge is spectral structure of experience interacting with deep nonlinear learning trajectories. That same bridge links category learning, induction, and neural representational geometry in one mathematical story. If you want, next we can make a sequel focused only on one technical segment, either the random matrix phase transition proof or the hierarchical diffusion spectral derivation, line by line. For now, this completes the full in-depth video for arXiv 1810, 10,531.